All right, thank you. Yes, so as mentioned, I'm a third-year grad student at MIT, and this morning I hope to tell you about the recent progress we've made on this physical cryptographic warhead verification protocol for nuclear disarmament treaties. So as some context, nuclear warhead verification, as we know, is a political and a technical challenge, and global warhead stockpiles are still estimated to be about 15,000 warheads worldwide, primarily in the US and Russia. So that's a lot of warheads to eventually, hopefully, get rid of. Any future disarmament efforts are probably going to require some sort of mechanism for verifying that the US and Russia, mostly, are complying with the treaties. However, you very quickly run into a problem in this case, and that's what I call the disarmament verification problem, in that it is very difficult to reliably identify a warhead as actually authentic without revealing any classified information in the process as to why it's authentic. So that's where we come in with our work on the MIT Physical Cryptographic Verification Protocol. So to start with, I'll go into a little bit more detail on the protocol, following up on Areg's slide. So it's a type of physics-based cryptography that uses a template verification system. So you start with your golden copy. Maybe you pick it from an ICBM, and through chain of custody and other records, you know that it is a real warhead. And you want to make a comparison of a bunch of candidate copies of the same model of warhead and determine whether they match. So you go through your list of warheads, you check whether A0, your golden copy, is equal to A1, your candidate, is A0 equal to A2, A3, and so on and so on. And if they are, you can send them to a dismantlement queue. Now the challenge in all this is to perform these checks. As Areg mentioned, there's the completeness, soundness, and zero knowledge requirements. So you need to protect the secrets without relying on software barriers that could, in theory, be hacked or bypassed. You want to make sure that you're not accepting any fakes into the dismantlement queue and counting those warheads against the treaty requirements. And you also want to make sure that your type 2 error is much less than 1. So the challenge here is to satisfy all these requirements with a physical process. And the physics process we use is transmission NRF. So transmission, or nuclear resonance fluorescence, or NRF for short, is used to make isotope-specific measurements of the warhead. So NRF describes an incident photon with energy corresponding to the energy level difference between two energy levels in a nucleus. That very specific energy of the photon can promote the nucleus to an excited state. The nucleus then decays very quickly, emitting a photon en route back to its ground state. And that decay can proceed either directly to the ground state, emitting a photon very close in energy to the initial photon, or through an intermediate state, emitting a slightly lower energy photon. But the important thing to consider here is that the emission energy of that photon is determined by the nuclear energy levels. So you get isotope specificity in an NRF measurement. So in a measurement, what this looks like, here I've shown some U-235 NRF emission data. It's a series of sharp emission lines sitting on top of a smooth continuum. And in fact, these emission lines are so sharp that you're only limited by the resolution of your high purity germanium detector. So let me back up to this slide. So if you were to make a measurement that looked like this of a real warhead, those emission lines tell you not only the presence of, say, uranium-235, but also the amount of uranium-235 in the warhead. So a direct measurement would end up revealing quite a bit of classified information about the warhead. So to avoid that, we don't make a direct measurement, we make somewhat of an indirect measurement. It's, as mentioned, a template verification scheme. So to begin with, we have a Bremsstrahlung interrogation beam. Now, if I ignore the warhead for a second and just imagine this foil here, this foil contains all the same isotopes that are in the warhead but in unknown amounts. Direct interrogation of the foil will give this kind of emission line spectrum. That is what is seen in the high purity germanium detector. And because ultimately the final measurement is it contains no sensitive information. Everything on this side of the dotted line, including the final spectrum, is available to the inspector, whereas everything above the dotted line, the warhead and the foil, is classified by the host. So that's the foil. Now if I put the warhead in the beam, it essentially acts as an attenuation mechanism. So the foil, you can consider will produce the initial height of the lines, and the warhead will bring them down in varying amounts depending on what exactly is in the warhead. This came out a little distorted, but again, I just want to emphasize that the final signal is somewhat of a convolution between each weapon and the foil, and you can use this to make a template measurement for your golden copy, your candidate, and compare the two final spectra. This, as Vavrek mentioned, essentially acts as a physical hash function. The encryption in this case is therefore done by a physics process and not by electronics or software. So about a few months ago, we first proved this physical cryptographic concept in JANT4. So we took a model warhead based on the Black Sea experiment, put it into JANT4, fired a Bremsstrahlung photon beam at it, and traced tens of billions of particle trajectories through the warhead. Some of them went on to induce NRF in the warhead, some of them made it through and induced NRF in the foil, and we looked at all the photons emitted in roughly the backwards direction of the foil as our final signal. And with that, I'll jump right to the results. Or sorry, let me back up first. We also looked at not just the genuine warhead, the Black Sea model, but also a geometric hoax, which I'll get into a little bit more later. But it basically mimics the series of on-axis attenuations due to the different components of the warhead, so that at its initial orientation, it provides the same final signal due to all the exponential minus mu x all being the same. So with that, I'll now go to the results of these simulations. Oh man, wow, that's distorted. Okay. So the graph should not look like that. That's interesting. But the whole point of it is that if you were to look at the proper graph, the black curve shows the NRF spectrum for the authentic Black Sea type warhead, and the red curve shows the NRF spectrum when we remove the valuable weapons-grade plutonium and replace it with depleted uranium. So this simple replacement produces very large discrepancies in some of the uranium-238 and plutonium-240 NRF lines. That doesn't work. But in this very simple scenario, we get something like 127 sigma discrepancy in tens of minutes of experimental beam time. Now, since we have so much isotope sensitivity, we might consider a more strict test. So what if instead of depleted uranium, we replace the weapons-grade plutonium with reactor-grade plutonium, which is, somewhat of a small isotopic shift, but still using the same configuration, same beam time, we still see a 7 sigma discrepancy, which is quite promising. As mentioned, we also looked at geometric hoaxes, which again mimic the attenuation profile along the Bremsstrahlung beam axis. So by design, in its initial unrotated configuration, which I chose to exactly match the Black Sea warhead, it's undetectable. However, rotation by even 10 degrees is sufficient to give an 8 or 9 sigma discrepancy. So the way we take advantage of this in the CONOPS of the measurement is we choose the initial orientation randomly, so that if there's a geometric hoax designed by a nefarious host, the chance that it exactly lines up correctly is vanishingly small. So we wrote up these results, published in Proceedings of the National Academy of Science earlier this summer. So now I'll move on to some more recent work. So simulations are great, but eventually we would like to perform an experimental demonstration. So to that end, we've been working on some basic tests of NRF at the High Voltage Research Lab at MIT. So here is our lab with me for scale. We have a 2.5 MeV electron accelerator. The electrons are bent by 90 degrees and impinge on a copper and gold radiator. This produces our Bremsstrahlung beam. Now the beam next interacts with our DU target, which we're using to take DU data, and NRF interactions are induced in the DU target, and some of the NRF photons are emitted into our high purity germanium detectors, which are sitting in this lead castle. We also established a few additional diagnostics. In particular, we set up a LISO gamma ray detector. It's a very fast gamma ray detector that we can use to make a direct measurement of the incident Bremsstrahlung beam, or at least the part that is transmitted through the DU target. And finally, at the very end, we set up an X-ray imager. So with the imager, we can actually see the spatial profile of the Bremsstrahlung beam and perhaps any fluctuations in it. So early results have shown us that we can very easily see the three major uranium-238 resonances at 2.176, 2.209, and 2.245 MeV. And we can also see their branch decays, 45 keV below each of the main lines. So this is, again, where the excited state of the nucleus decays not directly to the ground state, but to a 45 keV intermediate state in the first, before the ground state. So we see the uranium lines, but we also took data for aluminum-27, which is very useful for normalization. The energy here is at 2.212 MeV, which is very close in energy to the depleted uranium lines. And this allows us to make relative measurements, which I'll show later, to attempt to cancel out some of the systematic uncertainties in the measurement. So at the same time we're doing these experiments, we would like to have an analytical model for the count rate we should expect to be seeing in these experiments. So over the past couple months, I developed a simplified model of the physical cryptographic measurement using NRF. So to start, we have a parallel beam, the Bremsstrahlung beam incident on a rectangular warhead, so that's an approximation there. The transmitted beam through the warhead then impinges on the foil, NRF interactions are induced, and some of the NRF photons are emitted towards a detector and perhaps attenuated by a filter to reduce the overall count rate in the detector. So the model I showed in the previous slide actually gives quite good results for the relative measurements. So that's where we're taking the ratio of the aluminum line at 2.212 MeV to the depleted uranium line at 2.209 MeV. And so in theory, we should get a ratio here, depending on the exact experimental configuration, of about 4.70. That's a ratio of count rates, again, per microcoulomb of delivered beam charge. And in the experiment, we're seeing something like 5.5 plus or minus 0.8. So we're within 1 sigma statistical fluctuations. So that's a good sign to begin with. We've nailed the physics understanding, most likely, and now we just need to sort out some systematic effects for some absolute measurements, hopefully later on. So at the same time as all this, we're also working on validating the JANT4 code that simulates NRF. So previous results from PNNL, about 6 years ago, I think now, showed that the simulation code matched theoretical predictions to about 20%. So here I'm plotting the NRF count rate detected as a ratio of simulation to analytical predictions. And in general, the simulation is about 20% low. However, with our simplified model that I showed a few slides ago, we're seeing something closer to 5% agreement, which is a very good sign for the status of the Monte Carlo code. So here I'm showing the NRF count rate per million incident photons for a simplified flux model for the 3 different uranium-238 lines as a function of the foil thickness X. So this is here with no intermediate target, no quote-unquote warhead in the way. The thin foil, where I put a millimeter of depleted uranium in between the foil and the bremsstrahlung shows also very good results. But the thick target analytical models might need a few corrections for something like a centimeter of uranium in the beam. And I can get into those in the questions or offline if you're curious. So with that, I'll move quickly on to the future work. So I mentioned briefly we'd maybe like to do absolute count rate predictions for an NRF experiment. And as everyone in the past has found out, and as we've recently found out, this is very difficult to do. So currently, on the left here, our depleted uranium count rates are about a factor of 1.5 low compared to the analytical predictions. And on the right, our aluminum results are also about a factor of 1.5 low. So this similar factor of about 1.5 suggests that there's probably somewhere a systematic discrepancy in the transport of our photon beam. So whether that's the model of the initial bremsstrahlung beam or a geometric acceptance or a dead time that we didn't account for, that will take a bit more work. So the additional diagnostics I mentioned in the slide showing the lab can help point us in the right direction. I'm not sure if these points are visible in the back, but these are the count rates versus observed current in the HVRL measurements for the high purity germanium detector and the LISO direct bremsstrahlung detector. And with the exception of 1 or 2 points, all the fluctuations about the linear trend line appear almost exactly the same in the high purity germanium as in the LISO detector. And they're measuring 2 completely different things. So this suggests that there are some beam fluctuations that we did not account for in the initial calculations. Finally, we would like to quantify some of the sensitivity of the measurement. So the previous results plus delta of the previous results for various deltas. So particularly with the simplified model, we would like to look at different cross-section evaluations. We found that the typical Gaussian approximation to the NRF cross-section can end up underestimating the counts somewhat significantly. And now that we're looking at different cross-section evaluations, we can also estimate an interesting effect where the temperature dependence that goes into the Doppler broadening of the NRF cross-section can actually have a measurable effect on the final count rate. Additionally, we will look at different bremsstrahlung beam configurations. So whether you're interrogating a small part of the warhead with the bremsstrahlung beam or the entire thing at once, that's something to investigate. And in the same vein, whether you slightly misalign the golden copy of the warhead in the bremsstrahlung beam versus the candidate, whether that decreases your sensitivity significantly. And lastly, we'll look at diversions of small amounts of special nuclear material. So if I skim off some plutonium from the outside of the pit, and similarly, more elaborate hoaxes that might be able to fool the system into thinking that a warhead is indeed real. So with that, I will conclude by saying that the physical cryptographic verification technique we've been working on at MIT is very promising, and there are still, of course, several remaining technical challenges to resolve. With that, I'll take your questions. Thank you.
A new plant's been built. This is a combination of gaseous diffusion plants closing, particularly in France and the US, and also increasing expectations for LEU demand given the nuclear renaissance that was talked about